All right, so let's work another problem with conjugate B. This one wants values at various places. First, it wants the slope at B, which is here, and the displacement at E, which is this free end. I think before we get started, I think let's just kind of guess what the deflected shape will be to kind of give ourselves some orientation. So I think with these ends, with the only loads being applied, these little cantilever ends, they're all going to go down. So I'm guessing that the shape will look something like that. So we should expect a negative displacement at E and a positive slope at B. And again, since the geometry looks pretty, it's a mirror image or symmetric, and the loading is symmetric too, that when we find our slope at B, the slope at D will be probably the same value but negative. And then, of course, the displacement at A should be the same at E. So we get a lot of information about this. Just kind of interested, what do you think the slope at C would be right in the middle? Probably 0. Would that be the maximum displacement in the beam?
No.
It'd probably be the maximum positive displacement will be the absolute displacement. I would think probably, maybe, I don't know, depends. But these end displacements might get quite large. And also notice that, as I mentioned earlier, the moment of inertia of the overhangs is half that of the mid. Okay, so the middle section is going to have very limited displacement. The ends are going to displace more because of that. Remember, in all of our displacement, we divide by E and I. So when we divide by something smaller, you should get a bigger displacement. All right, so that's just kind of a background. You probably wouldn't go through this whole process when you're working the problem. I would suggest kind of thinking about the displaced shape to give you, again, to get you going. But after that, better get to the problem, so we'll do that now. At B, I'm going to assume that I have a reaction that's up and a reaction at D that's also up. And I'm going to need to find those to draw my shear diagram. And my moment diagram. So I'm going to come over here to the right-hand side and I'm going to find those values. So initially I'm going to sum the moments at D, make sure it's in equilibrium. So by summing at D, I should be able to find By. So when I sum my moments at D, this applied force at 8 is going to be a negative moment. So that'll be 8 kips times 10 feet. And then I get all the way over here to this guy, it's going to be a positive moment. Force is 8 kips and the distance is 30 feet. And then I'll have By, which creates negative moment, with a moment arm of 20 feet. I think when that's all said and done, and you solve for By, you're going to find out that it's 8 kips. I'm hoping. Is that what it looks like to you?
Yes.
I say yes. Somebody check that for me. And then when I sum forces in the y direction and make sure it's in equilibrium, so I'll have By acting up plus Dy acting up, and then I'll have minus 8 kips and 8 kips again. And in that case, I'll find that Dy is also 8 kips. Is that okay? Get those values? Okay, with that, I can now draw a template. There's my left edge and my right edge. And then I'm going to have this reaction point to deal with on both sides. So with a quick construct of the template, or a template, I can use that to construct my shear diagram. What kind of shear is this on the end? That's negative shear, right? So you're going to start off at -8. There's no load, so there's no change. There's no load, so it's 0 slope. And then I hit By, which is 8, and I come up to 0. So I've got this little 8-kip negative shear zone. And then from 10 to 30, there's no load, so there's no change, so I stay at 0. Then I hit Dy, which is up 8 kips. There's no load, so there's no change. There's no load, so the slope is 0. And I get a section that looks like that. So far, so good? Now I draw the moment diagram. So again, I'll assume positive x. There's my positive moment. I'm really shortening this up because I know that my moment's going to start off and go negative. So what's the moment at the free end? 0. And of course it's here. So I know the change in moment over this area, the first 10 feet, is the area of this part of the curve, which is base times height. That's negative 80. So I should come down to negative 80. And then of course the slope is the value, which is constant and negative. So here's a constant negative slope. The change in moment between these 2 points is the area of the shear diagram, which is 0. So there's no change. And since the shear is 0, the slope of the moment diagram is 0. And then I get the change in this zone is the area of the shear diagram, which is 8 times 10, or positive 80. And that connects me back to 0. And since the value is constant, I have a constant slope, and it's positive, a positive slope. So there's my moment diagram. Okay? So now what do we do? Now the fun begins, right? Conjugate beam. So let's start with first the geometry. What do these free ends become? Free end becomes, in conjugate space, fixed. And what do these internal supports become? Hinges. So what do we get? A mess. So I've got a beam to a hinge, to a hinge. That looks nice, doesn't it?
Yes, there you go.
And then I have to apply to that what? The moment divided by E and I. Normally that's okay, but now our I value is not constant. We're going to have to account for that. So how do you think we should do that? Which I value do you want to divide by? You want to divide by the I for AB or the I for BD? Pick one. All right. No one's playing along today. Even after my dog story, I thought that would soften you up. It didn't work. Okay, we're going to do AB just because it comes first in the alphabet. So I'm going to divide by AB. So if I take my moment diagram and divide it by AB, what happens? Well, over section AB, absolutely nothing. Right? Well, what happens over section B to D? When B to D, it's what? So let me write a little number here. So actually the moment, whatever it is in AB, is equal to what? It's actually twice. Oh, sorry. Yeah, I had that right. It's twice the moment in AB is equal to the moment in BD. Right? You see that? So if you want to divide by this guy, then when you get to this section, how does that relate to that? It's two of them. So over this section, I'm going to have 80 divided by AB. Over this section, I'm going to have 80 divided by that, but that's equal to that. And 80 divided by 2 is 40. You guys see that? So now, my diagram looks something like this. So those parts are simply projected, and they're both going to be 80 kip feet divided by EIAB. And when I get here and I divide 80 by EIBD, and BD is 2AB, and I divide 80 by 2, I get 40 kip feet divided by EIAB. Now I have a common denominator of EIAB, but I've made the adjustment. So since this section is twice as strong, it's reflected by kind of the moment gets reduced. Now this is all negative moment, so what direction is negative load, up or down? It's down, right? So all these values, this loading looks like this. I just have to solve that problem. For what? What do I have to solve? Well, what's the slope at B? So the slope in the real beam at B is what in the conjugate beam? The shear. I need to find the shear at B. And then I need to find the displacement at E. So the displacement at E in the real beam is what in the conjugate beam? The moment. So I've got to find this reaction force here, which will give me the shear, which will give me then the slope, and then I got to propagate that over here and find the reaction moment. That's my statics problem. So I'm going to suggest we break this into different free bodies. Obviously, we can't solve this as one free body. So I'm going to pull out this section BD and solve it first, and then run everything over here to the right. So the first free body I want to draw will be just of section BD. And if I draw that, I'll get this. So there's my load. And that had a value of 40 kip feet divided by EIAB. And then I'm going to assume that on this side I have the positive shear at B, and on this side I have positive shear at D. First thing I want to find is the value of B. To make it easier on myself, I can make a concentrated equivalent force of that. So the area of the loading curve, it's rectangle, so it'll just be base times height. The base is 20, so 20 times that is what, 800? So the force becomes 800 kip feet squared divided by EIAB. And it acts halfway in, so that should be 10 feet from either end. I bet you can guess what the shears are going to be. this load is probably going to be distributed equally to each one, so I'd probably get a value of 400. But let's get the sign right. So to find the shear at B, I'm going to sum moments at D. So I'll assume right-hand rule, and I'll sum the moments at D. So about D, this force creates positive moment, and that's 800 kip-feet squared divided by EIAB, that's the force, and the moment arm is 10 feet. And then the shear at B creates negative moment with a moment arm of 20. So the shear at B actually is positive and ends up being 400 kip-feet squared over EIAB. And we know that the shear at B in the conjugate beam maps to the slope at B in the real beam. So there's our value. It came out positive, and that matches the fact that we thought it would be positive slope. So what is the actual value of that? So the shear at B, which is 400 kip-feet squared, I just need to divide by E and the I at AB. So first E, which is 29,000 kips per inch squared. I at AB, that's 400 inches to the fourth. And then I have to convert square feet. So there's 12 squared or 144 inches squared and a foot squared. That's a pretty small number. What is it? The 400s cancel, so it's 144 divided by 29,000.
0.00497.
0.00497?
Yes.
Everybody else get that? Or anybody else get that? Yes. That seems reasonable. Pretty small number. Okay? Now what do we do? Well, remember, I now need to navigate over and find the displacement at E, which is going to map into the moment at here. So I'm going to probably need to draw this as a free body diagram. To do that, I'm going to need to know what's happening at D so I can transfer it over. So what's going to be the value of the shear at D?
Can we say the slope at D is the negative slope at D?
Say that again?
Can't we say that the slope at D is equal to the negative slope at D?
Yeah, but I don't need the slope, I need the shear. Well, it is the slope. Right. Yeah. But I need the value of D, so when I draw my free body diagram for DE, I can apply that as a load.
Negative shear.
Right. So when you solve for this problem, you're going to find out that VD is negative 400 kip-feet squared over EI. Do I need to write that equation out? You guys see that? Maybe I should anyway. So if we go back and sum forces in the y direction, deal with this free body diagram, I've got the shear at B acting up, I've got the shear at D acting down, and then I also have my applied force, which is 800 kip-feet squared over EIAB. So the shear at D should be negative 400 kip-feet squared over EIAB. That should not be a surprising result for this free body diagram. So what I'm going to do is flip this up and draw the remaining free body diagram on another piece of paper. If I can do it. Having trouble. There we go. So let's flip that up and draw the free body diagram for that section. So what I have there, this will be the free body diagram for DE. In that case, so I've got the load applied something like this. So what I'm drawing is this piece right here. So I've got the force, which is 80 kip feet divided by EIAB. That's acting down. This segment is 10 feet long. Also, since the shear is acting down here, on the other side it would be acting up, but it is negative. So that means the shear is going to be down. Right? And that will have a value of 400 kip feet divided by EIAB. So that's the value we got at D. And now on this end, I'm going to assume positive shear at E and positive moment at E. Now this problem doesn't care about the slope, it only cares about the displacement, so all I have to find really is the moment at E. To help myself out here, I'm going to create a concentrated equivalent force. I'll call it F. I'm going to sum the moments from E, so I'll need this distance. I'll call it D. So we'll start off here. What is that force? Well, it's a triangle, so it's going to be 1/2 base, which is 10 feet, times the height, which in our case is 80 kip feet divided by EI, and that's for AB. So that's going to be what, 400? So that should be 400 kip feet squared divided by EIAB. The distance D, well, from the 0 end to the centroid is 2/3 the distance, 2/3 is 10. I'll just write that as 20/3. I don't want to carry the fraction. I'll carry the fraction right now and not the decimal. Everybody see that? 2/3 of 10. So with all that set up, I'm ready to find my moment. So I'll sum moments now about E. That's here on the free end. So starting there, I have my internal moment, which is positive. And both these forces are going to create also positive moment. So the first one, let's do the force first. So that'll be 400 kip feet squared divided by EIAB. That's the force times the distance, which is 20/3. And then the shear that got transferred at point D is also positive moment. It's also 400 kip feet squared divided by EIAB. Except its moment arm is 10. It's a lot of work, but we should see that the moment at E, it looks to be negative. I don't know what the value would be. You guys will have to figure that out for me real quick. That's 4,000. That's not. That's 6,666.66.
Correct.
Is that enough sixes for you? Is it really? Oh, okay. So 6,666.7 kip feet cubed. And it came out negative, and remember at the very beginning we assumed, we kind of sketched the deflected shape, and we thought the displacement would be negative, so that makes sense. And we know that the moment really transfers to the displacement. So what is our displacement finally? We need to do some work here. So 6666.7 kip feet cubed. Let's divide that by EI and convert it. So our E value is 29,000 kips per inch squared. The I of AB is 400 inches to the fourth. And then cubic feet, that's 1,728 cubic inches. That's 12 cubed in a cubic foot. And we can all see that kips cancel, feet cubed cancel. At inches to the fifth over inches to the fourth, that should be just an inch. I say 8.2 inches. No, 0.82 inches. I don't know. I'm guessing. What's the answer?
Yeah, 0.993.
Oh, 0.99. 0.993? Anybody else get that?
Negative.
Oh, of course, negative. Beautiful. That only took 27 minutes. Very doable in class. In the exam.
We're going to find a displacement C.
Are we going to do who?
Displacement C. Ask for that.
No. We could.
Speed thorough.
If we wanted to, yeah. I mean, Mr. Montgomery brings up a good point. Finding the slope at E wouldn't be very challenging. You just have to sum forces in the x direction. In fact, it's going to be 400 plus 400. It's going to be 800 inches. That would be really easy to do, but the problem doesn't ask for it, so I'll stop here. Yes?
Why is it on radians? The other one was?
Well, the units come out here in inches, right? Now, the slope comes out dimensionless. I didn't mark them off, but you'll see that kips cancel kips, feet squared cancels feet squared. I got inches to the fourth, inches. There's no unit. So, in this case, it'll be in radians. That's pretty small, too. 5/1000ths of a radian. That's pretty small. Okay, so any other questions about this? All right.